Hello students and friends. In this video let us discuss one of the most important topic, that is halogenation of carbonyl compounds. Okay. So here halogenation takes place in acidic medium as well as basic medium. That basic medium halogenation, we are very familiar with this. That is nothing but haloform reaction. A carbonyl compound which has a methyl group on reaction with the halogen in the presence of base that produce haloform and corresponding carboxylic acid. Here, this halogenation in the presence of acidic medium. Here, what are the difference here? This is the acid, this is the base. In the presence of basic medium, we will get the haloform, but in the presence of acidic medium, just we will get the alpha halocarbonyl compound. Okay, but in this case this acetone molecule is dissociated into two fragments, but in this case here only single molecule, just hydrogen is replaced by the bromine in this case. Now you see here acidic medium mechanism of the reaction in acidic medium actually. So here in this case, first of all, this acetic acid protonation takes place on this carbon group, and then here, so this one becomes acetate ion. This acetate ion here actually removes the proton. So here this electrons are transferred to this one. Here this O minus, this O becomes a OH. So totally we will get the enol. Okay, we will get the enol. Now here this enol attacks on the bromine. So like electrophilic addition type of reaction, in this case here this pi electrons transfer to this carbon. This carbon carries a negative charge. This negatively charged carbon attacks on the Br plus and leaving out the Br minus. Here Br minus, here loss of H plus. Those H plus and Br minus combines, so loss of HBr of course. So in this case here ultimately one hydrogen, that means here H plus is replaced by the Br plus. So here the resultant reaction, we can say that electrophilic substitution reaction. Okay, this electrophilic substitution reaction. Okay, in acidic medium actually. Here in acidic medium, so formation of this enol is a rate determining step. Okay, formation of this enol is a rate determining step, but not attacking of the bromine. Here the bromine molecule attacks on the enol. It's not a rate determining step. That means here if you take Cl2 or if you take iodine, the rate of reaction is same, because here attacking of the halogen is not rate determining step. But here formation of the enol is a rate determining step. For suppose in this case, if you take C double bond O, here CD3 and here CD3. This one has a less rate of reaction than the CH3COCH, because here the formation of the enol involves a breaking of the CH bond. Okay, and now here CD bond is a stronger bond than the CH bond. That's why here there is a less possibility for the formation of the enol. Okay, that's it. So in this halogenation reaction, if you take either bromine or chlorine or iodine, rate of reaction is same. If you take CO, that means acetone CH3COCH3, or if you take C double bond O, CD3 and CD3, which of the following is which one is more reactive? CH3COCH3 is more reactive, because the CH bond is a weaker bond. Okay, now here in case of the basic medium, that base first of all remove the proton. As a result here carbanion is produced. Okay, so the C double bond O here negative, carbanion is produced. This carbanion is stabilized by the resonance. As a result we will get the enolate. Okay, this is the enolate ion. Now here again, here this when these negatively charged electrons are transferred into the this pi system, this carbon carries a negative charge. This negatively charged carbon attacks in the Br plus, so we will get this compound. Okay, so here also again ultimately that H plus replaced by the Br plus. It is also alkophil substitution reaction. Okay, this is also alkophilic substitution reaction. But here the one different point is this replacement is not stopped at this stage. Why? Because here after replacement of these hydrogens by the bromine, this bromine acting as a minus hydro. These two hydrogens are far more acidic than these three hydrogens. Okay. Again here these hydrogens are far more acidic than this hydrogen. Why? Because by the replacement of hydrogen by the bromine here, there is a one minus I group is introduced. Because of the minus I effect here, acidic nature increases. Then here this reaction is not stopped at this stage. Then here again here removal of the proton will get the again it is attacked by the Br. Now and ultimately this hydrogen is a far more acidic than this hydrogen or this hydrogen. Okay, because of the here two electron withdrawing groups presence of the two electron withdrawing minus I groups here, this hydrogen is more acidic. So ultimately here that hydrogen is also replaced by the Br. So I'll finally that three hydrogens are replaced by the three bromine atoms. Okay, now in this case, so by adding excess of the base here, OH minus attacks on this alkophilic carbon, transfer of this pyracons takes place. And next year, leaving of this CH3Br. Okay, because it is a good leaving group actually in this case. So CBr3 minus is stabilized by the three minus I groups as well as the d orbital resonance. Here negatively charged, this electron density is transferred into the vacant d orbitals of the bromine. So it is stabilized by the d orbital resonance as well as the minus I effect of the bromine. So here carboxylic acid. Now in this case carboxylic acid is acidic in nature. Here H plus transfer takes place that ultimately becomes a bromo form, and this is the carboxylate ion. So this is nothing but a haloform reaction. Okay. So this reaction is not stopped with one hydrogen replacement. All alpha hydrogens are replaced by the bromine in basic medium. Okay, but in case of the acidic medium that successive replacement reaction is not possible. Why? Because in this case here actually here this protonation takes place. Okay, in with acidic acid here H plus donor, so protonation takes place on this one. Now in this case here this one acting as a donor, that means here base, here the basic nature of this oxygen is decreased by the minus effect of the bromine. So actually here H plus attacks on this one. So for the attacking of the H plus, this basicity decreases step by step. Here in this case here, completely CH3 group, it is electron donating group. This oxygen is more basic than this oxygen because presence of the minus effect basic nature. That means electron density on the oxygen decreases. So it is acting as a poor electron donor. So it has a less tendency to get the proton from the acid. That's why here that does not produce the enol readily. That's why here further halogenation decreases. Of course, and at strong, that means under drastic conditions, halogenation takes place further. Okay, but at normal conditions here, monohalogenation takes place only. Okay, because that minus I group decays the basicity of that oxygen. Okay, see this one. In case of the acidic medium, in case of the acidic medium here in this case these hydrogens can be removed. Here these hydrogens can be removed in the enol formation. So here two enols are possible, this OH, okay, or this one OH and this one. Okay, which enol is more stable? This enol is a stable. Why? Because it is a more stable. Here in this case here three alpha hydrogens, here three alpha hydrogens, six alpha hydrogens, but in this case here only two alpha hydrogens. So this enol is a more stable enol. That's why here that this enol is formed in this course of reaction. So ultimately here these hydrogens are replaced by the bromine. Okay, that's it. But in case of the basic medium, that base remove the more acidic hydrogen. That means here these hydrogens can be removed by the OH minus, because here this is a primary carbon and this is secondary carbon. The primary secondary carbons here, primary carbanion is more stable. Here in this case we can see like this here. Double bond over here, negative charge. double bond over here, negative charge. Between these two, this is the more stable carbanion. That's why your base remove the proton ultimately from this one. But in case of the acid medium, here we have to consider the enol stability. So this enol is more substituted enol, so that's why it is the more stable. Through this enol reaction takes place. Ultimately, we will get this product. Okay, that's it. Now here for suppose we can write the product here. In acidic medium bromination, so here C double bond O, here in this case Br. Okay. So for suppose in this case acidic medium at more substituted carbon bromination takes place. So here in this case this hydrogen replaced by the bromine. Okay, now in this case this compound is oxidized to the carboxylic acid. Primer alcohols in the presence of acidic medium is oxidized. So here in this case, this carboxylic acid on treating with PbR3Br2. A PbR3Br2 is this reaction is nothing but HVZ reaction. So it becomes a C double bond O here, Br, and here this is converted to again enol actually. So here this one becomes a OH, this one is a Br, this is the double bond. Okay, so this is converted to enol actually. Now this enol form is attacked by the Br. Okay, like this here. This carbon attacked by the Br plus. So here as a result, so here Br and double bond over here Br and followed by hydrolysis. So in a hydrolysis step that Br is replaced by the OH because acid halides are more reactive. That means here by adding water that acid halides are converted to just carboxylic acids. Of course, here next in this case, so just here this hydrogen replaced by the chlorine. So what is the role of the sodium carbonate actually? So side product is HCl. That HCl is neutralized by the sodium carbonate. In this case here PCC. PCC means here this group is converted to aldehyde group. And then here halogenation takes place. So here there is a different type of reactions in this case. This aldehyde. In the presence of acidic medium, so alpha halogenation takes place. Double bond O here H. In acidic medium only monohalogenation. Then here in this case followed by nucleophilic substitution reaction. So this is a carbanion. This carbanion attacks on this carbon. So leaving out this bromine takes place. So SCET. This is the nucleophilic substitution reaction. In this case NaOH excess Br2. So here there is a methyl group here. This methyl group is converted to bromoform. Remaining part is converted to carboxylic acid. So double bond over here ONA. Okay. And next here. In this case here. In the presence of basic medium, all two alpha hydrogens. Because here this hydrogen is a far more acidic active hydrogen. So again here in basic medium, all alpha hydrogens can be replaced by the bromine. That's it. So here this compound also by adding excess of the bromine here, these two alpha hydrogens can be replaced by the bromine. We will get the tetrabromo compound. But if the same compound on reaction with the Br2 in the presence of acidic medium, just here monohalogenation takes place, double bond O like this. Okay, but in basic medium further substitution takes place. Okay, so here this one also again here there are two possibilities for the enol. So actually here two types of enols are produced. Here OH pi bond, here double methyl group. So based on the enol stability, we can write the further product. Here between these two, this enol is more stable. Then it is attacked by the Br2 molecule. Ultimately, we will get this product as a major product. Now in this case here, the Br2 in the presence of acidic medium. So actually that this hydrogen replaced by the bromine in acidic medium, followed by reaction with the base. You see this one. The very interesting one concept. Why? What is the role of here LDA actually? So in acidic medium, the replacement takes place Br. Now here, what is the role of LDA? Here, by using LDA here in this case, here these hydrogens can be removed. That LDA also base lithium diisopropyl amide. So carbanion is produced. So in this case, what are the advantage of this LDA? LDA is a strong base. So here, the total concentration of this compound is converted to carbanion. Now here, this is attacked by the Cl2. Okay, C double bond O, CH2Cl. Okay, that is the product actually. Here in this case here, that LDA at minus 78 degrees centigrade, so monohalogenation takes place. That's it. And next here in this case, in a basic medium. So first of all, Cl2NaOH means here the basic medium. So halogenation, that means haloform reaction. It is, so haloform is produced. That means here ONA plus CHCl3. Now this one reaction with methyl alcohol in the presence of acid medium. That means here that carboxylate ion is converted to carboxylic acid and followed by reaction with methyl alcohol is a esterification reaction. Okay, C double bond O, here it becomes a OCS. Next here, followed by reaction with LDA. That LDA, lithium diisopropyl amide, remove this proton. Okay. So here double bond O, OMe. And this is the negatively charged carbon. So here, now this is attacked by the Cl. This negatively charged carbon attacks on the C plus. Ultimately that H plus is replaced by this one. So this is the product. Next in this case here, first in acidic medium, one hydrogen replaced by the Cl. In a basic medium, another one hydrogen replaced by the bromine. This is the product. Okay, next here, this is another type of reaction. The carbonyl compounds on reaction with the PCl3, we will get the Gem-dihalide. Okay, it's not an alpha halogenation. That carbonyl group is converted to Gem-dihalide. Of course, this is the mechanism of this reaction. So generally here PCl5 exists as PCl4 plus and PCl6 minus. So PCl4 plus attacks on the C plus. So by multiple steps we will get this Gem-dihalide. Thank you for watching. Please share the video and subscribe my channel for more videos.